lesson that we have for the year, and this lesson we're going to be talking about tangents of a circle. So we're going to start by just defining what a tangent is, and then go on to how to construct one and talk about some theorems. So if we were in school, we would kind of just give you a circle and ask you to see if you could draw a tangent based on this definition. So a tangent is a line in the plane of a circle that intersects the circle in one and only one point. So basically, it's a line that touches the circle or a circle at only one point. So if you take a look here, this would then be a tangent because it only touches the circle right here. The other two segments that we really talked about or need to discuss would then be this is a chord, right? The chord touches the circle at 2 points. And a secant is one that touches the circle in 2 points but extends outward of the circle. So we have a tangent, a chord, and a secant. Okay. For today's lesson, we're only going to focus solely on some tangents. So this was a question that came up on a Regents exam, and they had asked to construct a line tangent to the circle at point O. And to do this, we're just going to walk through it kind of quickly. I know that some of you probably don't have your compass and your straight edges, or you should have a straight edge because you can use anything, but really you probably don't have your compass. So basically, when we're talking about a tangent, it's a line that has to touch the circle at only one point. So if they only gave us in this question OA, so from here to here, we can figure out how to draw a line so it only touches A and is kind of like perpendicular to A. And the way we would do that is by constructing actually a perpendicular bisector. So what we do is we first create, I did this way, a longer line, and we say, okay, so from O to A, I want the perpendicular bisector, so it has to be in the middle, so I'm going to flip this around, and then this here gives me now a segment O all the way to this point here, and A would be in the middle. I want A to be in the middle because I want a line to go through A, so then I would do the perpendicular bisector. So I would go a little bit past A, I would open up, right, I'd swing my arc above and below, I'd flip it around, I'd go to my other endpoint, swing an arc above and below, and then where those arcs intersect, I take my straight edge and I connect. Now this is then a tangent because it touches circle O at point A only, and it's a line, so I put my arrows at the end. Okay, that's how you can kind of incorporate constructions within the tangent. So now let's talk about common tangents, and I really like this. I think that they're fun. So common tangents, or a common tangent, is a line that's tangent to two circles. Now the circles can be the same size, they can be different sizes. They don't have to be anything specific, but what they have in common is a tangent. So we gave you some circles, and here they are. And now here are two circles. And we say that they have how many common tangents? So they have 1, 2, 3, 4. Each of the 4 lines only touch the circles at one point. So these two circles here have 4 common tangents. These two circles here that are actually tangent to each other only have 3 common tangents. They have one here, and one right in the middle. There it is. These two circles that are overlapping only share 2 common tangents along the outsides. These common tangents that are tangent from the inside only have 1 common tangent. And these concentric circles, and concentric means that they share the same center, don't have any common tangents. Okay, so this is all about common tangents. So how many lines can you draw that are tangent to each circle? And remember, tangent means it only touches each circle at one point. Okay, so here we have it. All right. Now, tangent segments. So when we say tangent, we're talking about a full line. But if we're saying a tangent segment, that's just a segment of the tangent line. So specifically, what a tangent segment means is it has to go from the point of tangency to an external point. So for instance, right here, we say that AC is a tangent segment as well as BA. Now, do you notice anything about AC and AB? They both share A as that external point of tangent, or that external point, and they're both tangent to the same circle. And when that happens, there's a really cool theorem that comes with it. And it's that any tangent segment that's drawn from the same external point, they're going to always be congruent and equal. So what that means is that AC is actually equal to AB, or AC is congruent to AB, right? So whatever the length of AC is, let's just say it's 2, well, then the length of AB is also 2. Okay, so you're talking about the same circle. If they share the same external point and they're tangent segments, then they are congruent. And I really like that theorem. It's super helpful. So now we can take that theorem and look at a question like this. And it says, given the following diagram, and they give us some information, AF is 10, CE is 20, BD is 30. Find the lengths of the sides of ABC and show that it is a right triangle. So let's do one thing at a time. Okay, so we're going to use that we have points of tangency here at F, D, and E of the same circle. So here's the idea. A is an external point. So A to F and A to D are tangent segments drawn to the same external point. That means whatever AF is, AD measures the same. So if AF is 10, so is AD. Okay. Same thing down here. C is an external point. F and E are points of tangency. That means that from C to F is going to be equal to C to E. So they're each 20. I know they're 20 because it told me up there that CE is 20. And then finally, the same idea would work for external point B. So B to D, B to E, they have to be equal. And if BD is 30, that means that EB is also 30. Now, the second part is, well, show it's a right triangle. So here's my whole triangle, A, B, C. So I know from A to B is 40, from B to C is 50, and A to C is 30. So how do I show something is a right triangle? Well, we're going to go back to, if it is a right triangle, we're dealing with side lengths. A squared plus B squared equals C squared. Pythagorean theorem needs to apply. And if that's the case, I have 3 side lengths, 30, 40, and 50. I also have 3 variables, A, B, and C. I have to determine of these 3 side lengths what goes in for C. And remember, we say C is the hypotenuse, it must be the largest side. So I'm going to substitute in 50 for C, 30, and 40 for A and B. So I'm doing that over here off to the side. And when I do that, and I evaluate, the left side and the right side are equal. That tells us that our side lengths work in Pythagorean theorem. So if they work in the Pythagorean theorem, that means that, hey, triangle ABC must be a right triangle. And there you have it. Okay? So we're kind of incorporating tangent segments as well as Pythagorean theorem into this type of question. All right. Then we just are drawing 2 really straightforward things. We have a radius right here, and we also have a tangent line right here. And it says predict the following theorem based on what you see. So if you take a look at the way the radius and the tangent intersect, they form a right angle. That means that a tangent and a radius will always be perpendicular. A tangent will always also be perpendicular to not only a radius, but a diameter as well, right? So a tangent is perpendicular to the radius of a circle. It's also perpendicular to the diameter of a circle. Okay, just something to keep in mind. All right, and then finally we have this little proof. So I know many of you are like, oh, proofs, I don't really like proofs, and I know. So what we're going to prove here is that if we have this diagram, this is not going to work. If we have this diagram with these 2 tangent segments, AB and CA drawn in, how do we prove these 2 triangles, ACO and ABO, congruent? So here are some statements that are made, and we said that AC is congruent to AB. That's true. And we know that because these are tangent segments drawn to the same external point, right? They're both drawn to point A. So that means that they're congruent. So there's our reason. Tangent segments drawn to same external point are congruent. All right, then it says over here, we have that OC and OB are congruent. Well, that's obviously true also. We know that's true because if I take a look, O to C and O to B, they're both radii. And in a circle, all the radii are congruent. So all radii of the same circle are congruent. Perfect. So think back to when we did proofs. What do we now have? We'll have a pair of sides here, another pair of sides here. So I either need an angle or a side. I chose to be really straightforward and go with the reflexive property. Right here, they both share side OA. So OA is congruent to itself by the reflexive property. That's another side. So now the two triangles are congruent by side, 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 side. So that finishes up our proof there. Okay. And to finish this off, we're going to just take a look at another example using kind of that same diagram. So here's this diagram, and basically what happens here is if we have the two tangents drawn to the same external point again, and we connect or we make a segment from that external point to the center of the circle, we just decided, well, hey, these two triangles are congruent. We proved that by side, side, side. What also happens is that this angle out here formed by the two tangent segments winds up getting bisected. So this piece is equal to this piece, this angle and this angle. The angle over here formed by those two radii are also congruent because this angle gets bisected. But if you think about it, if we prove that these two triangles are congruent, which down here we just did, what's the next step that we always says happens after triangles are congruent? And if you can jog your memory, it was C, P, C, T, C. Corresponding parts of congruent triangles are congruent. And if that's true, that means that this angle corresponds to this angle. Well, that's on the next slide. We said that those are congruent. And we said here, this angle is congruent to this angle. Well, that's true. And then we said, well, hey, then this must be congruent to this. And technically, we knew this even before we started because this is a radius with a tangent. And we said up here, hey, the tangent is perpendicular to the radius. So this is a right angle and this is a right angle. Okay, so this lesson really doesn't just go in terms of drawing in tangents. We're dealing with triangles and triangle congruency and the different relationships, how we kind of mold everything together into one. Okay, so this is just another, based off of that theorem, another thing that we know that this angle here gets bisected, so we have two equal angles. This angle here also gets bisected, so we have two equal angles. Okay, and then we have this here, and if we have a tangent drawn and then have a chord drawn in, so a tangent and a chord, we could also find the relationship or that angle measure formed by the tangent and the chord. And I made this kind of straightforward, and I just drew in the diameter with the tangent because we said since the diameter, when we have a diameter and tangent, they're perpendicular, so we knew this had to be 90 degrees. And I did that for a reason because you know that this is 90, but we also know that this is half a circle, so it's 180. And I did that so you can kind of see the relationship easily. If this is 180 and this is 90, well, 90 is half of 180. So that's the relationship between the angle and the arc when you have a tangent and a chord. So the measure of an angle formed by a tangent and a chord is equal to half the measure of the intercepted arc. So it's similar to an inscribed angle, like that relationship of half, but it's different in terms of how it's drawn or how you get that angle. Okay. And here is just another example to show you how to find with the tangent and a chord. So here we gave you that this arc is 280, and you had to find the measure of angle CAB, so this angle right here. So if this is 280, I know that this arc over here, minor arc from A to B, is 80. because the whole circle is 360, so 280 minus 280 subtracted from 360 is 80. That means that the angle formed by the tangent and the chord is half the arc. So half of 80 is 40. So this angle BAC is 40. So find the measure of angle CAB, or measure of angle BAC is 40 degrees. Okay, I think that's it, yeah. So that kind of finishes up what we have for our tangents. And again, this goes along with, we kind of discussed how to find an angle measure. We talked about relating in some proofs. We also discussed having common tangents, or tangent segments drawn from the same external point that are equal. A diameter and a tangent, or radius and a tangent, will always be perpendicular. And also how to find common tangents as so, or how to draw in common tangents. Okay. So this, like I said, is the last formal lesson that you will be watching. From here forward, tomorrow you'll have a Castle Learning assignment that you'll have Thursday and Friday the ability to complete. And everything must be handed in and submitted by June 19th, which is next Friday. Next week, we'll probably have some fun activities, things to do, give you a chance to make sure that all of your e-school grades are accurate and everything's handed in, any questions you have, and things of that nature. So I hope you have a good weekend, and remember, tomorrow, Castle Learning, you'll have those practice questions to try, and you'll need to look back at this lesson possibly to help you answer some of those questions. Okay. Any other questions, please remember, just email me or send me a message through Google Classroom.